Hi everyone, this is Srikanth S, Assistant Professor of EEE Department. In this session, I'm going to discuss the problems on DC motors. Now, first let us go with a 220 volts 4-pole series motor with 600 conductors, wave connected, supplying a load of 7.5 kilowatts by taking 35 amperes from the motor. Calculate the developed torque and shaft torque if the flux per pole is 15 milliwebers and its armature circuit resistance is 0.5 ohms. Now the given data is V is equals to 220 volts, the number of poles is 4 and number of conductors Z is equals to 600. If it is wave connected, the number of parallel paths A is equals to 2 and the output power is 7.5 kilowatts. We can write it as 7500 watts. And IA is equals to 35 amperes and flux is equals to 15 milliwebers, which is equals to 0.015 webers, where armature resistance is equals to 0.5 ohms. The developed torque is given by torque is equals to 0.159 phi z into Ia into P by A Newton meters, which is equals to, if we substitute all these values into this equation, that is 0.159 into 0.015 into 600 into 35 into 4 by 2, where TA is equals to 100.17 Newton meters. And the back EMF is given by EB is equals to V minus IARE, which is equals to 220 minus 35 into 0.5, which is equals to 202.5 volts. Now the back EMF is given by, we got the back EMF and then EB is equals to, from this we can calculate the speed. EB is equals to 5 Zn by 60 into P by A. So which is equals to 202.5 is equals to 0.015 into 600. Here 202.5 is equals to 0.015 into 600 into speed n into 4 by 60 into 2, which is equals to, speed is equals to 675 rpm. And the shaft torque is given by TSH is equals to output power in watts divided by 2 pi n by 60, where TSH is equals to 7500 by 2 pi into 675 by 60, which is equals to 106.10 Newton meters. Now the next problem is a 440 volts 14 poles lap wound DC shunt motor takes 1550 amperes from the supply. There are 280 conductors. Effective diameter of armature is 1.3 meters and the active length of each conductor is 0.33 meters. The value of average flux density is 0.7 Tesla. Calculate the value of torque developed and the speed of the motor, where V is equals to 220 volts, the number of poles is 4 and Z is equals to 280 Lap wound number of parallel paths is equals to number of poles, and diameter D is equals to 1.3 meters. Diameter D is equals to 1.3 meters and length L is equals to 0.33 meters, and B average is equals to 0.7 Tesla, which is equals to, we need to calculate the armature torque and speed. So here flux per pole is equals to B average into pi into dl by P, which is equals to 0.7 into 3.14 into 1.3 into 0.33 divided by 14, which is equals to 0.0674 Webers. Neglecting the shunt field current and voltage drop in the armature, the back EMF developed is obtained as EB is equals to V, which is equals to 440 volts. Now the developed torque is given by TA is equals to 0.159 into phi z into IA into P by A Newton meters, where T torque is equals to 0.159 into 0.0674 and 280 into 280 into, here the number of, here it is 1550 is the current, and P by A is 14 by 14, which is equals to, armature torque is equals to 4651 Newton meters, and speed of the motor N is equals to EB into 60 into A by 5ZP. If we substitute all these values, 440 into 60 into 14 divided by 0.0674 into 280 into 40, which is equals to 1400 RPM. Now a 115 volts shunt motor has an armature whose resistance is 0.22 ohms. Assuming the voltage across the brush contacts is 2 volts, when the armature current will flow, what is the armature current will flow when the counter EMF is 108 volts, and if the motor load is increased so that the counter EMF drops to 106 volts. So we need to calculate the armature current when the counter EMF or back EMF is 108 and 106. So here armature current is equals to VA minus EB or EC, that is back EMF divided by RA amperes, where IA is equals to armature current, VA is the applied voltage, EC is counter EMF or back EMF, EB back EMF, and RA is equals to armature resistance, where IA is equals to 115 minus 2 minus 108 whole divided by 0.22, which is equals to 22.7 amperes. And armature current at 106 volts is same, 115 minus 2 minus 106 by 0.22, which is equals to 31.8 amperes. Now if we take a 6 pole 30 slot DC commutator generator has a lap wound armature winding, and the armature constant Ka is 9.55. The generator is operated with a separately excited field such that the field flux per pole is 0.04 Webers per pole. The generator is driven at a speed of 3000 RPM The no load armature voltage is 418.9 volts. Now the above generator is now operated as a motor. The flux is 0.04 webers per pole and it is desired to supply a load requiring a torque of 50 Newton meters at 4000 rpm. Now the armature circuit resistance is 0.075 ohms. Calculate A, the back EMF, and B, the required armature current and voltage to supply this load, where EB is equals to Ka phi V, that is equals to 9.55 into flux value is 0.04 into 418.9, which is equals to 160 volts. The armature current can be found directly from the following equation, that is TD is equals to Ka phi Ia. So from this, Ia is equals to 50 by Ka phi is 9.55 into 0.04, which is equals to 130.9 amperes. The necessary armature voltage is V is equals to E plus or minus IARE, that is equals to 160 plus 130.9 into 0.075, that is 160 plus 9.8, that is equals to 169.8 volts. Now in a motor, the armature resistance is 0.1 ohm. When connected across 110 volts mains, the armature takes a current of 20 amperes and its speed is 1200 rpm. Determine its speed when the armature takes 50 amperes from the supply mains, when the field current is increased by 10%. A speed is equals to K into V minus IARA by 5, where S2 by S1 is equals to same K into 110 minus 50 into zero point 0.1 divided by phi 2 whole divided by K into 110 minus 20 into zero point 0.1 whole divided by phi 1. Here 105 by phi 2 by 108 by phi 1, which is equals to 105 by phi 2 into phi 1 by 108, where S1 is the 1200 rpm, where S2 is equals to 1200 into 105 by 108 into 1200 into 105 by 108 into phi 1 by phi 2. But here phi 2 is given as 1.1 times the phi 1. So if we substitute in place of phi 2, we will get the speed. In place of phi 2, if we substitute 1.10 into phi 1, that is equals to 1.10 into phi 1. So the phi 1 will get cancelled. We will get the speed as 1061 rpm. Now a 25 HP 240 volts series motor takes 93 amperes when driving its rated load at 800 rpm. Now the armature resistance is 0.12 ohms and the series field resistance is 0.08 ohms. At what speed will the motor operate if the load is partially removed so that the motor takes 31 amperes? Assume that the flux is reduced by 50% for a current drop of 62.66 into 2 by 3 percentage, and the breast voltage drop is 2 volts at the both end. We need to consider here the speed is equals to V minus IARA by Ka phi. That is, if we substitute these values, that is 800 is equals to 240 minus 2 minus 93 into 0.12 plus 0.08 whole divided by k into 5 Fl. That is Sx is equals to 240 minus 2 into minus 31. Here the current is reduced by 31 amperes into 0.12 into 0.08 whole divided by k into, here the flux value is reduced by 50%, 0.5 into 5 Fl, where Sx by 800 is equals to 232 by 0.8 divided by k into 0.5 into Fl, which is equals to divided by whole divided by 219.4 by kfl, k5fl. 5fl will get cancelled. 231.8 by 219.4 into 0.5. From this, Sx is equals to 1690 rpm. Now assume that the DC motor shown in figure draws a current of 10 amperes from the line with the supply voltage of 100 volts. If the total mechanical loss is 90 watts, calculate copper losses in the field, armature current, copper losses in the armature, total loss, motor input, motor output, and efficiency. Here, this is the data which is given. Armature resistance is 1 ohm, RF is given as 100 ohms, and IL is given as 10 amperes, and EG is equals to 100 volts. Now, from the given data, the copper losses in the field are IF square into RF, that is 1 square into 100, that is 100 watts. And the armature current is 10 minus 1, which is equals to 9 amperes. And copper losses in the armature are Ia square into Ra, that is equals to 9 square into 1, which is equals to 81 watts. The total loss is 100 plus 81 plus 90, which is equals to 271 watts. The motor input is EA into IL, which is equals to 100 into 10, which is 1000 watts. The motor output is equals to input minus losses. 1000 minus losses are 271, which is equals to 729 watts. And the efficiency is output power by input power into 100. That is 729 by 1000 into 100%. That is equals to 72.9%. The nameplate rating of shunt motor is 150 HP, 600 volts, 205 amperes, 1700 rpm. The resistance of shunt field circuit is 240 ohms and the total armature circuit resistance is 0.15 ohms. The motor has commutating winding and the armature reaction is neglected. We need to calculate the full load efficiency of the motor and the speed regulation. Calculate efficiency and delivered torque when the motor draws half load current from the line. If the motor is to deliver a full load torque at 1200 rpm, what value of resistance must be added to the armature circuit? Now at full load, the motor input is equals to Vi by 1000, that is 600 into 205 by 1000, which is equals to 123 kilowatts. The motor output is equals to 150 into 0.746, that is equals to 111.9 kilowatts. Motor losses is equals to input minus output, So here 123.0 minus 111.9. This is the motor loss, that is 11.1 kilowatts. Where efficiency is equals to 111.9 divided by 123 into 100, which is equals to 91%. Now the losses are here, the shunt field losses are 600 into 600 by 240 in the all divided by 1000, that is equals to 1.5 kilowatts. And armature copper losses is equals to I square R in by 1000 kilowatts, that is equals to 6.15 kilowatts. 6.15 kilowatts. Now the stray power or remainder is given as 3.45 watts. The total losses is equals to 11.10 kilowatts. Now the no load current to the motor will be that required for the field and stray power loss. That is, no load current is equals to 2.5 plus 3450 by 600, that is equals to 8.25 amperes. The generated voltages are Eg is equals to 100 minus 205 minus 2.5 whole into 0.15, which is equals to 569.6 volts. Now Eg at no load is equals to 600 minus 8.25 minus 2.5 into 0.15, which is equals to 599.14. Hence the no load speed is equals to 1700 into 599.1 all divided by 569.6, which is equals to 1790 rpm. And the speed regulation is equals to 1790 minus 1700 whole divided by 1700 into 100, which is equals to 5.3%. This is the speed regulation which we are going to get. The delivered torque at full load is 463, and obtained from the horsepower equation, the developed torque is 478, and which includes the stray load power loss. Here the stray load power loss is 5.3%. In this session, I have discussed some problems on DC motors. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.